All right, so now what I want to do is take our first real look at the kind of stuff that we're doing that we're dealing with in this business and economics focused calculus class. We're going to keep seeing these specific types of functions that we use specific letters to denote throughout the course, starting from here. And the first one is what we call a cost function. So in this case, we're thinking about a company or a manufacturer specifically that produces some kind of a product. And what we want this function C of x to represent is the cost to the company to manufacture these products. Specifically, it's the cost of producing X units of whatever that commodity is. So if I want to produce 1,000 units, then I would plug 1,000 into the function, and the output would be the cost to me as the manufacturer to produce those things. In other classes, you spend a fair amount of time talking about how to come up with different models for this function based on all the things that are taken into account for cost to a company. So for example, there's materials cost to produce whatever the product is. There's labor costs, there's facility maintenance if you're running a factory or something like that. All of that is factored into this function. We are just interested in analyzing this function once it's already been determined by somebody else. So we're not going to spend time looking into exactly how to come up with the C of x function. It's just going to be given to us. Okay, so for this example, suppose that there's a manufacturer that produces wallets, and the cost of producing X wallets is given by this cost function. C of x equals negative x squared plus 2,000x plus 45,000. Okay, and in this case, in pretty much all the examples we look at, cost is going to be measured in dollars as opposed to cents. What we want is the average rate of change of cost when the number of wallets produced per week is between 500 and 525. And then we also want to interpret that answer, okay? So we're going to do this the same way that we've been doing it. It's the change in our output over the change in our input. So really what I want for this average rate of change is I want the change in my cost, which is C of something minus C of something, over the change in my input, and my input is wallets produced, so the change in wallets produced. We're going from 500 to 525. This determines the interval that we're working with. So 525 goes in here, 500 goes in there, and then down here, 525 minus 500. So output, input, okay? At this step, I can start plugging some stuff in. So I'm going to have negative 525 squared plus 2,000 times 525 plus 45,000 minus, and then again, remember, you have to put this second function in parentheses so that you're not just subtracting that first term. Negative 500 squared, just plugging 500 into that function, plus 2,000 times 500 plus 45,000, okay? All of that goes over 525 minus 500, which is just 25. Now, as before, you can plug this into a calculator right away as is, or you can simplify some stuff to make the stuff you have to enter into your calculator a little bit less. So we once again have a constant here, 45,000, minus the same constant here, 45,000. Remember, the minus will come in and change all of these signs. So these 45,000s are going to cancel out right away. We never even have to put them into our calculator because together they just make 0. And then if I look at what's left, I have this negative 525 here, minus negative, so that make squared, sorry, that would make it a plus 500 squared here. And then I have 2,000 times something minus, because that minus will distribute, 2,000 times something else. We can factor that 2,000 out. And then what's left in here would be 525 minus 500, which is just 25. Okay, so some of this math, if you do it mentally, you can really like minimize how much stuff you have to calculate. I can do more steps to simplify this, but I don't really care to. I just wanted to do a little bit. Now I can start plugging things in. If you plug this into a calculator, you're going to get 975. This time, though, there are units involved. So I want to make sure I'm including those units in my rate of change. It's output units per input units. And again, output units in this case are dollars. Input units are wallets. So I could write dollars per wallet, but normally we would use a dollar symbol, which goes to the left of the number. So I would just say $975 per, I'm going to use this symbol for per wallet. Okay. So that's the answer, but it also asks us to interpret that answer. What does this mean? Well, notice the wallet is singular. So what this is saying is that on average, as we produce between 500 and 525 wallets, the cost to the manufacturer is about $970 for each of those wallets that you're producing. Okay, so let's put that into words. On average, it costs the manufacturer $975 per wallet to produce between 500 and 525 wallets. Okay, something like that, but that's how we're interpreting this. It's not a total of $975 for all of these wallets. It's $975 per wallet for each of these 25 wallets that are produced in this interval right here. Okay. All right. So this next example is also not a business and economics example, but it's a good one to kind of get some variety in what we're looking at. So once again, we're looking at rates of change. It says a nurse measures a patient's heart rate in beats per minute, or BPM, in 30-second intervals over the course of 5 minutes. And these measurements are recorded in this table below. So this top row here is the time at which these different measurements are taken, 0 seconds, 30 seconds, 60 seconds, and so on. Down below, in the second row, we have the heart rate at those different points in time. And what we want is the average rate of change in this patient's heart rate during 2 different time intervals. The first one is over the last 2-minute period. So again, remember, every time we jump from one entry to the next, that's 30 seconds. So 30, 1 minute. 30 more seconds, 2 minutes. So from 180 seconds to 300 seconds, that's the last 2-minute interval that's being talked about here. So if we want the average rate of change in heart rate is the output, which means time is the input. We put the change in our output in a numerator and the change in our input in a denominator. So finding those values here and here, from 180 seconds to 300 seconds, the outputs are 87 at the end of that interval minus 110 at the beginning of that interval. And then down here, I'm going to take the difference in time. So 300 minus 180. Do this either by hand or in a calculator. I'm going to do it in a calculator, and I'm going to give you an approximate answer because it comes out to a really long decimal. We get approximately negative 0.192. We need units because this is an application problem. So my output units are BPM, beats per minute. My input units are seconds. Okay? Let's make sure we're understanding what the negative means here. Remember, the negative in a rate of change means that your output variable is decreasing as your input variable increases. So in our velocity example, as time increased, our ball was getting closer to the ground. So the distance between the ball and the ground was decreasing. Here, this is meaning that on average, over the course of that last 2-minute period, the patient's heart rate was slowing down. It was decreasing. Okay, that's what the negative here is telling us. And not only that, it was decreasing at a rate of about 0.192 BPM per second. So each second, on average, it was slowing down by about 0.192 BPM. Okay. Next, let's look at the same thing, but this time a different time interval. So between 120 seconds and 240 seconds. So we're doing the same thing. The change in BPM, which would be 85 minus 89, over the change in time. So that's 240 minus 120. And same thing as before. So this goes into a calculator. This comes out to approximately negative 0.033. And same units. We're talking about the same type of rate, just over a different interval of time. So we're seeing over the course of that time interval as well, a decreasing heart rate on average at a rate of about 0.033 BPM per second. Okay, so these are not decreasing at the same rate, and what that's indicating is that the patient's heart rate is not increasing or decreasing at a steady rate. It's kind of fluctuating, so these averages are coming out different over different time intervals. Okay, all right. Up until this point, when we've been dealing with rates of change, it's been exclusively talking about these average rates of change. And at the beginning of this section, we said with that velocity example, our goal was actually not to find a average rate of change. What we wanted was what's called an instantaneous rate of change, which is the exact rate of change for an exact input, not an interval of inputs, but an exact input. So the velocity example, we wanted to know the speed of the ball at exactly 3 seconds. We didn't know how to do that, so instead we took the velocity of the ball over a 1 second interval starting at 3 seconds, so from 3 to 4 seconds. That was just an approximation for the exact velocity of the ball at 3 seconds. But then we mentioned that we can get better and better approximations if we make that time interval smaller and smaller. That is going to kind of be the thing that motivates how we find this instantaneous rate of change. Okay? So let's look at an example where we might have to approximate a little bit more closely what the instantaneous rate of change would be for, a given function. So in this example, we have a company called Ugly Mug, and they make coffee cups. And we have this function R, which is going to represent the revenue. We'll talk about this function a little bit more later. But it's going to represent the revenue that this company makes for selling X coffee cups. So how much money are they making in just revenue? And this table here is some inputs and outputs for this function. So if we sell 527 mugs, we make $1,965.71, right? And then we have these other values here as well. What we want from this is the average rate of change of revenue on these different intervals here. So first 527 to 530. It's the change in revenue. So we're looking for the output change over the input change. 527 and 530, those are these two columns here. So 527, 530. I'm going to take the difference in my outputs. So that's for number one, that's going to be 1961 minus 1965.71, And then we're going to divide that by the difference between these two values of x. So 530 minus 527. And we're just going to go right to the answer because we don't want to waste time doing a bunch of arithmetic. From a calculator for this, we would get negative 1.57. And remember, the units here are output units over input units, dollars per mug. X is measured in mugs. Okay? If I do this again for part 2, I'm going to get something similar. So again, this time, it's the interval from 528 to 530 mugs sold. So still using 530, still going to use this column right here, 1961 minus 528 would give me this output. So 1964.16 over 530 minus 528. Go to a calculator with this. This one comes out pretty close to what we see here, but not exactly the same. Negative 1.58, which we interpret as a negative $1.58 per mug. Okay. Same thing for number 3. This time a smaller interval, 529 to 530. So I'm using these two columns. 1961 minus 1962.59 over 530 minus 529. This one comes out to approximately negative $1.59 per mug. Okay, we have 3 more to go. All the same process. Let's do the next one here, number 4. Now I'm using the interval from 530 to 531. So I'm going to do 1959.39 minus 1961 over 531 minus 530. This, after plugging it into a calculator, is going to give me negative, I didn't leave a whole lot of room for this, negative, what did I get for that one? 1.63, so $1.63 per mug. And then 2 more to go, 5. So this time I'm going to use the interval from 530 mugs to 532. I'm using these two columns, 1957.76 minus 1961 over 532 minus 530. This comes out to negative 1.62, so $1.62 per mug is how I interpret that. And then finally, number 6, the interval from 530 to 531. These two columns, I have 1959.39 minus 1961 over 531 minus 530. This comes out to approximately negative $1.61 or $1.61 per mug. Okay, what is all this? What was the point of doing so many of these? Well, for the first 3, you can see that we're using intervals which have 530 mugs as the right endpoint of that interval, which means the left endpoint is a smaller number of mugs. However, as I go from 1 to 3, that left endpoint, 527 is what we started with, that number is getting closer and closer to 530. So 527, 528, 529, we're closing in on that right endpoint and making these intervals smaller and smaller. The other 3 intervals that we did this over, I'm still using the number 530, but this time I'm making it my left endpoint, which means my right endpoint is a number that's larger than that. But notice as we go from 4 through 6, that right endpoint is approaching 530. It's getting smaller and smaller. 533, 532, 531. It's closing in on 530 and making that interval smaller and smaller. So what's the point of this? Well, the fact that 530 keeps showing up indicates that what we're really trying to do here is approximate the instantaneous rate of change in revenue exactly when 530 coffee cups are sold. And so we're going to use the results here to approximate that. Remember, as this interval gets smaller and smaller, I should be getting a better and better approximation for this. So the smallest interval out of these first three is this last one. And that means I went from negative 1.57 to negative 1.58 to negative 1.59. This is the closest to that actual rate of change that I'm looking for. Same thing here. For 4 through 6, the intervals got smaller and smaller, so we had negative 1.63, negative 1.62, negative 1.61. This is going to be the best approximation out of those three. So if these are the two approximations that I'm getting, either as I approach 530 from the left or from the right, I would probably think that whatever the average of these two things is my approximation, and that would be negative $1.60 per mug. Okay, so that's my educated guess. Is that exactly the correct answer? We can't know for sure because we have kind of incomplete information since we're just using a table. But that's the most logical and reasonable thing to assume the instantaneous rate of change in revenue would be. Now, moving on from here. Did I skip a page? No, okay. So we can do the same thing when we're talking about those secant lines. Remember, we had a connection between the average rates of change and the slope of a secant line through a graph. So I'm going to do the same basic idea as what I did in that last example, but it's not going to be in the context of an application anymore. It's going to be in the context of slopes of secant lines. So suppose we have this other graph, f of x equals negative x squared plus 5x minus 3, and it passes through different points on the graph. Remember, a secant line is a line that passes through 2 points on a graph. Okay? So the first one we're going to look at is if it passes through the points where x is equal to 1 and x is equal to 2. I want to find f of 2 minus f of 1 over 2 minus 1. Remember, that's how we would find the slope of a secant line. Well, here's the function we're working with, negative x squared, so that would be negative 2 squared, plus 5x, so that's 5 times 2. Sorry, my dog's kind of whining in the background. Minus 3, and then I'm going to subtract from that the same function but with a 1 plugged in. Negative 1 squared plus 5 times 1 minus 3. And that goes over 2 minus 1, which that's just 1. Okay? Again, this can go directly into a calculator. But you can save yourself a little bit of work if you simplify things a little bit. So the negative 3 here minus this next negative 3, we know those are going to cancel. I know that negative 2 squared is negative 4. Be careful with this because when I don't have parentheses around that negative 2, then literally what this means is 2 squared, but then I make that negative. It's not the same thing as negative 2 squared. It's a little bit, it's a subtle thing, but it makes a difference. I also have this negative 1 squared, but then that minus will make that positive, so that's a plus 1. And then I have 5 times 2, but also negative 5 times 1. Remember, we can factor that 5 out and do 2 minus 1. So I'm kind of using a lot of the same tricks and stuff. You don't have to keep doing, you can plug this into a calculator at this point if you want to. This one's actually really easy to work out by hand, though. We get 2 in this case. So the slope of that first secant line, that's going to be 2. Okay? B. Now I'm finding the secant line through x equals 1 and x equals 1.5. So notice, same initial x value, but the right end point of the interval that I can think of these x values as making has gotten smaller. It's approaching that 1. So I would do the same process, but this time with 1.5 instead of a 2. F of 1.5 minus f of 1 over 1.5 minus 1. Same idea, except everywhere I plugged a 2 in up here, I'm now plugging a 1.5 in. So that's 5 times 1.5 minus 3 minus negative 1 squared plus 5 times 1 minus 3. These are all still 1s because I'm plugging a 1 in there. 1.5 minus 1 is 0.5. I'm just going to go ahead and you know, say that we did the work on this one, plugged the stuff into a calculator, this would have given me 2.5. For both of these answers, there's no units because, again, this is not an application problem. We're not talking about dollars and mugs and things like that. It's just a number when there's no additional context given. C, same idea, except now that right endpoint is 1.1. F of 1.1 minus f of 1 over 1.1 minus 1. I'm going to leave out this middle step. Hopefully you can see what's going to happen. Everywhere I put a 1.5 in this example, it's now going to be a 1.1. So I'm going to say equals ... Just saving a little bit of time here. This comes out to 2.9 once you do the arithmetic or the calculator work there. So what is this saying? It says estimate the limit of the slopes of these secant lines as the right endpoint approaches 1. So as this number gets closer and closer to 1, what is happening to the slopes of these secant lines? Well, looking at the ones that we have, as that right endpoint gets closer to 1, we get a 2, and then a little bit closer, we get a 2.5, a little bit closer, we get a 2.9. It looks like this number is approaching 3. So just based on parts A through C, my guess would be that that slope is approaching 3. Okay. All right, we're going to stop this video here, and we'll talk about kind of where all of this is going in the next video.